Hi, I'm Dr. Ed Pollock, and the object that I chose for this activity is an integrated circuit chip, otherwise known as an IC chip. The reason I chose this is because an IC chip has a specific path and logic that has to be followed to get to our end result. As you can see in the middle there's a pinout for this chip that goes from 1 through 14. Most of the chips that I chose use the same thing. You can have more than two inputs except for a inverter or a NOT IC chip. The NOT is exactly what it is. It has one input and flips it to the opposite output, which is what a light would do. And how does this chip relate to me? Well, as you can see, pin 14 has your power, which you can put in my basic diagram. You can see that it goes from 3 volts to 15 volts as input. So we can look at that as the passion that the instructor puts into the topic that's going on. It doesn't have to be very passionate, just getting the message across. It's 3 volts. Very passionate, it's 15 volts. And we can change that off. So that is your power source coming in. On the other end, we need ground to complete the circuit. So that's pin 7. And that's the feedback that we reply back to our students. So that's how I see this working in a class setting. And so as you can see, if I take this basic input, pins 1 and 2 take input, and the input would be a value of either 0 or 1. And then the output is the result of the logic that the gate went through. So in essence, the IC chip that I put there in front of you is a 4011, which is a NAND, which is a not AND. So if we go and look at the AND gate with its truth tables, you can see that when you have a 0 and a 0, you get a 0 with an AND gate. When you have a 0 and a 1, you get a 0 with an AND gate. When you have a 1 and a 0, you get a 0 with an AND gate. And when you have a 1 and a 1, that's when you get a 1 or a true. So why did I use a NAND gate? Because what I wanted was the exact opposite. When I have a 0 and a 0, I want to get a 1. And when I have a 0 and a 1, I want to get a 1. And when I have a 1 and a 0, I want to get a 1. And when I have both of them true, I want to get a false. So that's the different way of doing that. And so you could say, well, I could use an OR gate. But as you can see, an OR gate doesn't work the same way. So I could use 1 or 2. So I could use an OR gate and maybe flip them, but it may not work. So the NAND gate gives me what I want to do, which that drives what the breadboard does up above. But before we get there, you can see that we have AND gates, OR gates, NAND gates, NOR gates, exclusive OR and not exclusive OR, and the not type ICs. So in order to build our sequence, I can build a sequence using whichever, all those gates or a few of those gates to get where I want, and students can add on and still get to the same result, even though they chose a different path on how to get there. So in my little breadboard example, when both of them are up in that position, we are not turning anything on, but we have power going to, so we have 2 1s going in, and we're going to get a 0, so the light, the red LED, is off. When I push both of them down with the NAND gate, the light comes on. When I have one of them depressed, the light comes on, either one. And when they're not depressed, then that. But there's the basic circuit. Can we rewire that to work a different way? Yes, and that's the whole point of changing the path. That's how our class flows. Not every student is going to use the same logic to get where they need to go, and they may get the same result at the end. using different logic chips. So I hope you enjoyed this. Take care.